Morning, everyone. Welcome to the next installment of the JKMRC Friday morning seminar series that take place here at the lecture theater, but also online, as is the case this morning. My name is Katerina, and myself and Karina are co-chairs organizing the seminar series this year. So before we start, on behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to respectfully acknowledge all traditional owners and their custodianship of the lands on which we all meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connection to country, and we recognize their valuable contributions to Australian and global society. It is our pleasure to introduce our today's speaker, Professor Simon Michaux, who holds the position of Associate Professor of Geometallurgy at the Geological Survey of Finland, also known as GTK, in Helsinki in the Circular Economy Solutions Unit. He holds a Bachelor of Applied Science degree in Physics and Geology from the Queensland University of Technology and a PhD in Mining Engineering from JKMRC here at UQ. He was also the recipient of the Ian Morley Prize in 2006. He has over 18 years of combined work experience in the Australian mining industry in research and development, working in the private sector, and even 3 years in Belgium at the University of Liège, where he researched circular economy and industrial recycling. So his work experience in Finland at the GTK also includes having worked in the minerals intelligence before joining the current unit. Simon's overall long-term objectives include the development and transformation of the circular economy into a more practical system for the industrial ecosystem to navigate the twin challenges of the scarcity of technology minerals and the transitioning away from fossil fuels, things that he will talk about today. So no word of a lie, it is 2 a.m. in the morning. So thank you so much for joining us and still saying yes to presenting today. The floor is all yours, Simon. Thank you.
All good. Okay, so, excuse me. What I'm going to show you today is a combination of two pieces of work. The first one was the report that Tim was referring to earlier, and the second half of the work is work that is in the process of being published. The title is Assessment of Extra Capacity Required of Alternative Energy Electrical Power Systems to Completely Replace Fossil Fuels. Before we actually get to the actual work, I'm going to show you a couple of patterns that I showed my management to convince them to do this work in the first place. These are the metal prices that the World Bank tracks to look at the health of the industrial ecosystem, the base metals, precious metals, and energy, oil, gas, and coal. Now, I've overlaid these metal prices to the number 100 and the month of December 2001. And so what I've done here is to show periods of relative stability. Now, there's two very important points to come up here. So we've got a relative period of stability, and in around 2005, we had a blowout. Now, this is quite important. The metal price is the handover point between those who extract metals from the ground and turn it into minerals from the ground and turn them into metals, and those who buy those metals and manufacture goods. So you're looking at the heartbeat of the industrial ecosystem. So I make a case that this blowout started with a chain reaction in the oil industry. And a major economic correction in 2008 was not enough to resolve the underlying volatility. So whatever this is, it is not speculation, it is structural. And so the industrial ecosystem's evolving, and this change started 17 years ago. It's not something that might happen in our future. So I took the same data, but now I've actually pinned it to January 1970 and the number 100. You can sort of see there's the pinpoint. We've got data back to 1960. And this shows the blowout of what actually happened when the United States currency decoupled from the gold standard. And a few years later, the 1973 oil embargo happened, and they were able to throw money at it to solve their problems just by printing money. So all currencies became fiat. And so that's zooming in right on that point there. So you can sort of see there's actually 2 points the industrial ecosystem has had quite a big change. So this is again January 1970 and the number 100, but this is just base metals. So this is to show, g'day Rick, how you doing? Yeah. Anyway, so this is just to show base metals. This is the mining industry. So these patterns can be seen in the mining industry as well. So you see a period of stability, but then we had the blowout in 2005. These are the energy resources, 1970 again. So you can sort of see it's a pretty clear pattern. So there's our blowout in 2005. And there's the decoupling from the gold standard, and there's the petrodollar. And that's zooming in on it. So, all right, so the system is changing. It is valid to look at this stuff. So we wish to replace oil. We're going to phase out fossil fuels. And when I came to Europe 7 or 8 years ago, I used to go to the European Commission and in Brussels and sit in on these meetings where the most amazing amount of money was actually put into these presentations, but they were all platitudes. There was no substance to any of it. Now, we actually want to phase out fossil fuels, and we want to transition away, and we want to replace it with a new system. There is very little understanding of what fossil fuels is doing for us now, like what is our dependency, and also our vulnerability to it. So this is actually the discovery of fossil oil back to 1900. And as you can see, most of the oil has been discovered in the decades past. And this tall part here is the Gawa deposit in Saudi Arabia, the largest oil deposit the world has ever known. The chart on the right is the same data, but now it's put in a cumulative percent curve. Now, this red is discoveries, and blue is production, and green is the difference between the two. Since our maximum point of net inventory add happened in 1985, and since then it's been declining. The other point here is half of all oil ever produced has been produced since 1992. So to actually zoom in on the last couple of years in particular, this is a study from Rystad. We've actually got, we're not discovering that much oil and gas these days compared to a couple of decades ago. And in fact, I've got a chart that shows that most of the time we're actually using more oil than we're discovering. So we're depleting. 81% of the existing producing fields are in decline, and they're declining at an average rate of 5 to 7%. Of the largest 10 modern producing fields, the youngest was discovered in 1976. So here's oil production at the moment. So as this is everyone. So as you can see, there is a peak in 2019, 2018, but this could be an artifact of COVID. To split it up, these are the countries that are actually still expanding. It's only 5 countries. However, everyone here, except for the United States conventional oil and the Canadian tar sands, they are expanding, but everyone else on this chart actually peaked in 2019. That could be an artifact for COVID. In fact, COVID has provided the perfect camouflage. We actually don't know, and we will not know for another couple of years. So, but if the United States and Iraq were excluded, then global oil production would have peaked in 2016. Everyone else is in decline, including Saudi Arabia. That's the pink line across here. So this is actually what we need to replace. And what this is showing is we don't have 50 years to get into this. We really need to get into it now. Here's where we're at the moment. So this is production and consumption. The current peak at the moment is November 2018. And then a few months later, we had COVID and the COVID lockdowns, and that has provided an artifact in the system that is just not sensible in any way, shape, or form. 2019 might be the last sensible year of data that we've seen for a long time. So since March 2020, though, demand exceeded supply 73% of the time. So here's oil price. Now, this has been adjusted for inflation. So there's a couple of points where we're bouncing between the oil prices too high for consumers and too low for producers. The oil price needs to be high enough for producers to be economically viable, but low enough for consumers to actually access that oil in terms of, in a way that allows growth to happen in the current system. So this is what I actually published in 2019 in my oil report. And so the idea was the oil industry window of viability was closing. And so how have things happened since then? Well, that's what we look like now. This grey band is the COVID pandemic lockdown. So I now split things up into eras. This pattern was created as a consequence of the blowout in the metals in 2005 market that I showed earlier. The chart on the middle is created as a consequence of a system held together with quantitative easing. And the third pattern has been created as a consequence of the lockdowns and the supply chain disruptions, which has completely cooked everything. So we've got multiple eras. So when we come out of the COVID pandemic formally, right, what will be another era again? Do we return to normal or what? No one knows what's actually going to happen. So that is the motivation to actually study what is this system replacing and what is the practicalities. So this is the report that I actually wrote. This actually started out as a short 50-page report, but my review panel kept giving me a hard time about things that were not included, and it blew out to the size it is now. So, okay, physical tasks that were done in industrially by fossil fuels, like what really happened here, and what was the true scope of useful work. So if we were to knock out fossil fuels, what useful work would have to be done in its place? So then I assembled all the non-fossil fuel systems that I could get hold of to actually replace the work in direct replacement that are actually industrially stable. And then I calculated the quantity of electrical power we would need to do all that, charge electric batteries, make the hydrogen, etc. Now, the original study had an energy mix the same as 2018, scaled up to the new capacity. Since then, and what I'm showing today is the next generation of energy mix that's based on an IEA projection. So in this report, we have number of vehicles by class, number and size of batteries, an understanding of when you'd use an electric vehicle and when you'd use a hydrogen fuel cell, estimates of both rail and the maritime shipping fleet for both electrical systems and hydrogen systems, which means you can compare the two, and how do we phase out power generation for, say, oil, gas, and coal, and heating. I also examined the possibility of expanding the nuclear power plant fleet. Like, is this possible? And the simple answer to that is we need the nuclear power fleet to expand a little bit, but it cannot replace fossil fuels. It will not expand in time, and we have issues of handling spent nuclear fuel at large volumes. So then there was an assessment of biofuels. Can biofuels save us? The answer is no. And plastics and fertilizers were looked at as well. So all of that is in one place, internally referenced. So what was the approach here? So we're going to phase out fossil fuels, and we're going to implement things as fast as possible. Faster the better. So much so it's going to be very difficult to predict. All other studies have looked at what we might do next year or the year after in terms of market implementation. There was no long-range planning at all. But there'll come a point when the existing system that you see when you drive to work each morning is fully replaced. That is, all power that you see is generated with renewable systems, and all vehicles will either be an electric vehicle or a hydrogen fuel cell vehicle. And after that, presumably, we would see economic growth once more. So I'm modelling that point there. Now, the European Commission, bless their cotton socks, would actually make a prediction like they wanted a 100% system replacement by 2030. They made this statement in 2017. 2030 is now 8 years away. It's not going to happen. So now they're talking about maybe a third of the system is going to be replaced by then. Now, a third of what? So we take the estimates of the full system, and then we can actually sort of carve it up in terms of time, whether it's practical or not. So this was the plan. So what does fossil fuels do for us now? How much will we need? And how many units are we looking at? But at the base of all of it is what quantity of minerals will be needed to do this. This all started with a cup of coffee with management in 2018. Yeah, you got to watch it when you have coffee with you guys, because they will listen to what you say and they'll wander off and do things like this. So what they wanted to know was what quantity of minerals and what kind of minerals will be needed to source the gigafactories of Europe, the planned battery gigafactories of Europe. And what seemed like an innocuous question at the time, it became very clear very soon that vast sections of information just simply was missing, or the information that was available wasn't in a form that was useful. So I dashed just to go off and fill in the gaps. And that was the first piece of work. The calculation arc went like this. So what was the true scope? To phase out fossil fuels. And so I looked at the internal combustion engine fleet, cars, trucks, rail, maritime shipping and aviation. I did it for the United States, Europe, China. Now this was interesting. I actually had a friend of mine who is Chinese, and she actually went to China and actually accessed a whole lot of government databases. And I actually got data from the Chinese government and then got it translated into English. And that was that was an experience, let me tell you. And the fourth calculation was the globe together, everything together. So there's 4 calculations running in parallel. And that gave us the number and size of required technical units. And the question of what proportional mix. To put this in context, in 2018, 84.5% of primary energy was still fossil fuel based, and less than 1% of the vehicle fleet was electric. So that means the vast majority of the system that we seek to replace has yet to be constructed. And as it's not been constructed, we can't recycle it. The first generation, at the very least, has yet to be manufactured, and it will have to be sourced from mining. Now, this very, very basic question really shocked the European Commission guys. They had not put 2 and 2 together. And so that went to the required power grid expansion. They needed a number of batteries. There was also the issue of required power storage to manage intermittent supply. Wind and solar are highly intermittent, and at the moment, the gas industry is the buffer. I'll talk a little bit about this later, but you remove the gas industry, we need a new buffer. And so even at a very, very conservative estimate of what is needed, that power storage system is much, much larger than like 30 times larger what the electric vehicles will require. If you couldn't be bothered reading the report, just read this little black square here. Current plans are not large enough in scope. The task before us is much larger than the current paradigm allows for. The baseline calculation went like this for the globe. There'll be 1.4 billion vehicles. Now that estimate is low. It's probably close to 1.5, maybe even 1.6 by now. But that was what I was able to assemble at the time. That estimate of global vehicles, I couldn't find in a report. So I actually had to go out and estimate it myself. And that surprised me. The basics have not been done here. And that's it, because there's a lot of money being put into, getting people to do these sorts of studies, and they completely missed that. Anyway, those vehicles traveled a little under 16 trillion kilometers in the year 2018. So the whole system was modeled for being an electric vehicle, and the whole system was also modeled as a hydrogen fuel cell. So I was able to compare efficiencies, and I came up with this interesting concept. So an electric vehicle system requires a battery that is 3.2 times the mass of the equivalent hydrogen fuel tank. So what that means is, for the same energy storage mass, your hydrogen fuel cell can go 3.2 times as far, or will last 3.2 times as long. But hydrogen is not an energy source, it's an energy carrier. You've got to make the hydrogen. And if you're not going to use gas to do it, then you've got to fall back on electrolysis using electricity. And to do that, we needed 2.5 times the electricity to make the hydrogen compared to charging the equivalent electric vehicle battery system. So you put those two together and we get this. All short-range transport should be electric vehicles. Anything that stays in a city. All passenger cars, commercial vans, delivery trucks, buses, anything with a short range of, say, like 100 kilometers. They'll travel 14 trillion kilometers across a year. But to do this, we will need 65.19 terawatts of batteries. Now, this is where it gets interesting, because all other studies I've seen compare the quantity of batteries needed in terms of gigawatt hours. So I'm terawatt hours. One of us has got our numbers badly wrong. And so I audited the World Economic Forum, like, where did they get their numbers from? And it turns out they just plucked the numbers out of the air because they sounded good. They've badly misunderestimated the size of the global fleet, and that's how it's rippled out from there. All long-range vehicles should be powered by hydrogen fuel cells. All semi-trailers, Class H, HCV trucks, all freight that goes between cities in the rails. The entire maritime shipping fleet should all be hydrogen. Now, that's a conservative estimate, but we will need 200 million tonnes of hydrogen annually. That's our hydrogen economy. So here's our systems put together. That's the electric vehicle fleet. Those cars and those batteries, we will need that amount of power. This is the amount of power we need to phase out other industrial actions. And this is the hydrogen economy. Those vehicles travel that distance consuming that amount of hydrogen, but to manufacture it, we would need that amount of electricity. And it's now the bill's starting to mount up here. I looked at biofuels. Now, biofuels may be the most sensible way to keep the aviation industry going. It also could be the best way to keep the plastics industry going with bioplastics. We also may need the biomass industry to make fertilizer for petrochemical industrial fertilizers are becoming a problem in terms of land degradation. But so we're already pulling too much out of the environment at the moment. So we've got to have a genuine sustainability audit that has both economic sustainability, but also biodiversity sustainability boundary conditions in that audit. And at the moment, we don't have one. So we have to have a genuine discussion about what can we actually extract out of the environment. This is actually the punch-up that's happening in Finnish Parliament at the moment. The forestry industry here is as powerful as the mining industry in Australia. And so there's a great deal of arm wrestling over what can we actually harvest out of the forests. So let's put the electrical power systems together. These electrical power systems, this is actually on the low side, because most industrial action happens with the consumption of coal and gas on site, and then it's converted to energy on site. This is what's just been drawn off the power grid. So there's a vast amount of energy associated with manufacturing that is not included here. And that is actually a huge piece of work to include that. So these numbers I'm showing you are very much on the low side. So we're going to put it all together. We need 36,000 terawatt hours or thereabouts. That's a very low estimate. Now, if we use the energy split, which I'm going to show you in a few slides' time, we need to make 586,000 new non-fossil power stations of average size. Now, to put this in context, the current fleet's about 46,000. So we're talking about more than 10 times the number of power stations. Now, what's actually happening here is the energy return on energy invested for renewables is much lower than fossil fuels. That, unfortunately, is a reality. So if we put it through the split that I'm going to show in a couple of slides' time, this is what we end up with. Now things get interesting. So what I'm showing here is the power storage buffer. So wind and solar are highly intermittent. Supply and demand has to match. In the literature, they've got things like, to get through winter, we need 12 weeks buffer supply for the whole system. The reference I settled on was a 4-week window for the entire system, or the entire system across all power generation. But for the calculation, I settled on a very conservative estimate for just wind and solar only, and nothing else for 4 weeks to get us through winter. And that really low estimate was 548 terawatt hours. So these are the same numbers shown graphically. So this is what we've got at the moment. The column on the left is electrical generation in 2018. So that's what we can use. The white is what we want to phase out. And the green on the right is what we are going to phase in if we're going to keep the system the way it is. The tasks are Yes. So that was the power generation in 2018. It's 26,000 terawatt hours. So we're talking about making an electrical power system substantially larger than the existing power system with energy that's very expensive and fragile. The tasks are charge the electric batteries, produce the hydrogen for the fuel cells, phase out oil, gas, and coal power generation, heating of buildings, and a sliver along the top is to phase out coal-fired steel manufacturing. Some back-of-the-envelope calculations about what industry is consuming for gas and coal as feedstocks on site appear to be this another 36,000 terawatts on top of this. Now, I've yet to actually get those numbers together, but this is looking like very much a lowball estimate. So this is our task. They're the physical tasks on the left, and we are boiling down to, say, 36,000 terawatts. So for now, let's take this number and use it. So the ARENA organization has actually released a report predicting what the energy split's going to be in 2050. And so this is an estimate. It's very brave of them. I'll take it. So I'm going to take the energy split for 2050 to predict what might happen in the future, and I'll add some of my own assumptions that I learned from the first report. So the assumptions are all fossil fuels will be phased out. Hydro will expand by adding an extra 115% compared to 2018 production rates, as in it will expand. Nuclear will double in capacity compared to 2018. Biowaste, we can't really expand it beyond what it is now because it's looking like we're actually over our skis and what we're harvesting from the environment. So any extra biomass could be a problem. So in my calculation, I've assumed the biomass combined heat and power plants will stay at their current capacity. Geothermal generation will triple. In Finland in particular, we are looking at putting a network of holes for geothermal heating of buildings every 20 meters across Helsinki, and that will heat the buildings. And if we can do that, we can actually take that power off the grid. So after the above calculations, all remaining new capacity will be split equally between solar and wind. That is what the IEA believes will happen. So any new wind capacity will be split between 70% onshore wind turbines and 30% offshore. That is, again, an IEA recommendation. And new solar capacity will split between 90% solar photovoltaic and 10% solar thermal. Again, that's an IEA projection. And this is what we end up with. So these are the percentage splits across the power systems. So there's no practicality here. This is what they think, this is what they think would like to happen. So this is how we get 586,000 power stations of average size. So I collected some information about what the power stations of each of the different systems actually did in 2018. Not what they said they were going to do, what they might do in the future, but what do they actually do across a year. Solar and wind, for example, are both only operating 25% of the time. The rest of the time they are idle. And that's just an unfortunate practical reality. So this was the power produced by an average single plant in 2018. Nuclear is our best performer, but nuclear is at the end of a very complex value chain. And so I did a simulation on that. There are difficulties in expanding the nuclear system. So the International Energy Agency believes that they're putting their hopes on in the future for wind and solar, which happen to be not very good compared to everything else. So if we want to deliver 1,000 terawatt hours a year using these systems, you could use 142 coal-fired power stations or 30,000 solar PV arrays or 12,309 wind turbine arrays of average size, where each array is like 10 windmills. This is where we're getting the extra numbers from. So each of these sites will have to be built and constructed and maintained, and then when they wear out, they need to be decommissioned. So renewables have a much lower energy return on energy invested ratio than fossil fuels, and the real truth is they may not be strong enough to power the next industrial era. So gas and hydro are power generation has to balance with demand. Supply and demand has to balance, otherwise the grid will age. This is a snapshot of Canada, problems in Canada for a couple of weeks. And as you can see, it goes up and down. Power demand goes up and down. At night, we demand less power. And so they have to regulate this. So the orange is nuclear, and nuclear can't really move much because of the nature of what it is. Coal behaves the same way. They are able to regulate hydro, but within a narrow bandwidth. So wind and solar are along the top as well. Wind is the green and solar is the yellow. And as you can see, they both vary greatly. Wind in particular varies all over the place. The maximum wind generation happened to occur in a demand valley. So to make up the buffer, they use the gas industry. Gas can be turned on or off at will. Remove gas, and we need a new buffer. Now, there's a few ways we can look at our buffer. There's things like flywheels and molten salt. But in terms of application, ease of application, all our strategic planners, both in Europe and the United States, believe or think that they're going to use stationary battery storage facilities. So, but this is what we need. So wind and solar. So here is solar radiation in Germany across the year. We don't get as much sun in winter, and that's just reality. So solar is varying not only on a day-to-day basis, but also in a seasonal basis, and it's also vulnerable to when it's overcast. So it's actually all over the place. Wind varies as much as quite a bit in a week-to-week and month-to-month pass. We need at least 4 weeks buffer storage for industry to be operating reliably, or things like a smelter. So based on that calculation, the power that we need, and according to those splits, 34% will be solar PV and 38% will be wind. So if we need 4 weeks buffer, that's how we get our 548 terawatt hours. Now, this is the elephant in the room. It is mentioned in the literature every now and then, but it is not part of the discussions when they pass platitudes amongst themselves when they're talking about the circular economy. They're very vulnerable. A lot of the studies being presented are only a piece of the pie, and or they've got the very edge of it, and for that reason they can't see that they're actually facing the wrong direction. So in South Australia, we've got the Hornsdale Power Reserve, which is a 100 megawatt capacity. This is one that Elon Musk very famously put in. So this is what the European Union is now using as the standard to talk about. It's been done in Australia, we can do it here. So in the global system, we would need 15,635,478 such stations across the planet in the power grid system just for that 4 week buffer. So, and that is actually about 30 times capacity compared to the entire global electrical vehicle fleet. So the market for batteries is actually substantially larger than currently understood. Right, so that's where the first report finishes, and the next report now starts. This is a paper that's being published. It's in peer review at the moment. So the purpose actually is to calculate how much metal we will need to produce one generation of these renewable technology units to phase out fossil fuels. So the IEA released a report quoting how much metal is actually in each unit. So, and they also released a series of things of estimates in the market in 2040. What would the market share look like for battery chemistries? Things like light-duty vehicles and heavy-duty vehicles, but also in power storage as well. And so across the chemistries. And then the battery chemistries themselves, there's an estimate of the metal content for each one. Now, these calculations are quite crude. For example, there are many variations within each class, but at the level of the global fleet metal content, this is just fine. So these numbers that I got from this were projected against the numbers at the end of the last report. And so this is solar panels. So again, the same thing. Most of the solar panels in 2040, like about 90%, will be silicon-based. crystalline silicon. I could not get data for the cadmium telluride or any of the other systems. So my assumptions for my report were all solar panels are crystalline silicon. And that's an assumption. That's 90% of the market as projected to be in 2040. So this is the number of technology units that we now need to manufacture. So these are the electric vehicles and their batteries. These are the hydrogen fuel cells, trucks, freight locomotives for rail, and the maritime shipping fleet. These are the wind turbines. And these are the solar panels, and down the bottom is the power storage buffer. So I've put together an example to show where these numbers came from. So let's look at wind turbines. How did I handle these numbers? So you start out with what's the capacity required in the global system, the market share of units, what different units will be, number of units by type as estimated on the capacity required, metal content for each unit type, and the sum total for the global fleet for bimetal type. That was the calculation circuit that's been done for each of the systems looked at, and it was all summed together at the end. So here is our split that we're using. So we're going to look at wind. So we have an estimate of terawatt capacity of wind both onshore and offshore. So we take that capacity that we need over here. We then take the power produced by a single average plant in 2018, like what did they actually produce? And that gives us the number of plants that we will need to deliver that. And the average installed capacity for those plants was 37.2 megawatts. And so that gives us the number of new annual capacity required. And then that can be split up into, if everything was a 3 megawatt turbine, how many turbines are we looking at? And so that gives us the number of units that we need. So then we have the IEA report that told us in 2040, the split between, we've got four possible units for power generation, electric wind turbine systems. So what is the market share for both onshore and offshore? And then we have the metal content of each of those units. So the units are DFIG and PM and what have you. So these is what they mean. So like GB DFIG is gearbox, double fed induction generator, and so on. So this is the onshore market, the split that we've got projected against the needed capacity, and that gives us the number. And so by megawatt, we've got metal content by megawatt, and that's the offshore systems. So we estimate them separately and then we combine them at the end. So now vertically, we've got the 4 units across here, and then we've got the metal content per kilograms per megawatt, where we've summed everything together. So now we've actually got the resolution of what metal is needed to produce a single unit of a wind turbine per megawatt. So then we can actually sort of, well, for the onshore system, the total amount of metal that we will need for the number of wind turbines and the metal content, and we end up with this column on the far right, which is the total metal content by metals. And we did the same thing for the offshore systems, onshore and offshore, and then we sum them together. And so then we actually get to this point where we get these sort of 2 columns here. Metal quantity required for onshore wind turbines for the global system, metal quantity required for the offshore systems. That's a typo there, that should be offshore. So there's the wind turbines. This is metal content for solar panels. Metal content to construct the needed nuclear power plants, hydro plant construction, and then the second part of the table is geothermal power plants. They all have to be constructed. And then we get to the units. Electric vehicles, this is what we will need to go into the electric vehicles. And I was able to estimate the platinum going into the hydrogen fuel cells, just the platinum. I couldn't get any of the other information. And then we get to the batteries for electric vehicles and batteries for stationary power storage. And these numbers are huge, you might notice. And so we're going across not just your classics of cobalt, lithium, and graphite and nickel, but now we've got everything else as well. And again, this is a crude estimate, a very crude estimate. The real numbers will probably be larger, and yes, it'll be more complex, but for now, this will suffice to make a point. So then it all is summed together. So everything we need is summed together per metal, and that gives us this column here. Total metal required to produce one generation of technology units to phase out fossil fuels. And so that we've got these numbers here. The next column is global metal production as it was from mining in 2019. So this is all from the USGS and the BGR. The final column is how many years of production at the 2019 rate would be needed to hit the actual volumes needed. So 2019 is the last year before COVID. It's the last year of stable data. That's why I've used it. So you might notice some of these numbers are rather large. Like we will need 7,101 years of production to produce the needed number of volume of vanadium. That's your redox batteries. So the idea that we're going to do this in 7 or 8 years is very amusing. So then the question is, oh, we'll just open more mines. It's simple, right? So here are those same numbers compared against reported global reserves. So there's the amount of metal we need, and there is the global reserves. This column is the proportion of metals required to phase out fossil fuels as a percentage. That is, of all the copper we need to make one generation of units, current global reserves will get us 19.23% of the way there. We don't have enough copper for one generation. Now, here's the amusing part. Each of those technology units have a life cycle. They last between 8 years and 25 years, at which point they have to be decommissioned and replaced. The next piece of work, which has been planned at the moment, is if we had a known number of units coming offline and we knew what was in them, if we put them through recycling systems, how much could actually come out the other side in terms of recycled metal, and compare that to what's required for its replacement. I expect it's going to be something like maybe 30% can be recycled of some metals, but not all. Right, and so that will actually show exactly what is the relationship between mining and recycling. You might notice all the battery metals of lithium, cobalt, and graphite, and what have you, are all less than 5%. So that is, global reserves, as stated at the moment, is less than 5% of what we need to generate one generation. The simple answer here is we will make batteries out of something else, like fluoride or sodium. We'll get off lithium-ion chemistry. And what we're trying to do is actually get the people around GTK to have this discussion. What would those alternatives be, and what minerals would they come from, and can we go and look for them, please? So, and these systems will be run in parallel, not instead of. We will need them all. Now, for those who think it's going to be easy, for every 1,000 deposits discovered, only 1 or 2 become mines. And the time to take a discovered deposit to a functioning mine is between 15 and 20 years. And for every 10 producing mines, 2 or 3 will go out of business because of market conditions. So this is not going to be easy. So this is actually to make a point. Prior to 2020, it's been estimated that the global system has mined 700 million tons of copper back to 4000 BC. So that's an estimate. But to keep economic growth on track the way they think, they will have to mine the same 700 million tons over the next 22 years. So here's where things get interesting. Current copper reserves are 880 million tons. So that's what, 30 years of production. So better get out there and get exploring. But we want 4.57 billion tons of copper, that is with a B, just to manufacture one generation of renewable technology. So this is more than 6 times the historical mined copper through history. And we need that for just one generation, and 20 years later, we do it all again somehow. So the message here is we need to look at this and maybe come up with a different plan. How's copper discovery been going? Well, for the last 15 years or so, not so good. These are the number of discoveries that have come online. This is not the volume, it's the number. So the number of strikes has been steadily decreasing at a time when we'll be putting more and more into exploration. So we've got a couple of trends coming together here, and reality is starting to bite. What's going on? So how do we get to this situation? Like, why do we need so much stuff, and how can we need so many hundreds and sometimes thousands of years of production? So here is all metal ores mine, and you can see most of it is iron ore in terms of mass. Inside this yellow square, we've got other metals like aluminium, manganese, chromium, and copper and zinc. And inside that little black square in the top right-hand corner is our technology metals. Right. Most of our systems so far, for the last 150 years, has been mined with basically steel and your basic metals like manganese and aluminium with the assistance of fossil fuels. Minerals are the new oil now, so we actually want the future to come out of this black square in the top right-hand corner. So we want the volumes at an unprecedented level that was developed in this brown and yellow squares to come out of the little black square. So this is the level of expansion that is required. Now, the nature of the minerals required for these technology metals, they're not found in bulk quantities like iron and copper. And that is the source of the problem of this difference in quantity. So what we're looking at, stewardship of planet Earth, this is the sort of things that we're actually now sort of having a frank discussion about. So we used to have, 500 years ago, a small human system, a big pile of natural resources, and a small pollution plume. An industrial ecosystem of unprecedented size and complexity that took more than a century to build, with support of the highest calorifically dense source of cheap energy the world has ever known, that would be oil, in abundant quantities with easily available credit and unlimited mineral resources. And now we've got a system that's a human system that's really large, a depleted natural resources portfolio compared to what we had, but we've now got a massive pollution stream. So now we seek to build an even more complex system with very expensive energy, a fragile finance system saturated in debt, not enough minerals, with an unprecedented number of human population embedded in a deteriorating environment. So at this point, I'm going to say this is probably not going to go as planned. Conclusions. Additional non-fossil fuel power is estimated at 36,000 terawatt hours. It's probably larger. Proposed energy mix translates into 586,000 new stations, which is more than 10 times what we have now. So as wind and solar sources are intermittent, we need power storage buffer. That power storage buffer with a 4-week capacity, we need 548 terawatt hours of battery capacity. This is about 30 times what the electric vehicle fleet will need. Path to transition away from fossil fuels is much larger than first thought. The energy return on energy investment ratio for renewable systems is much lower than the fossil fuel systems, and renewable energy may not be strong enough to replace fossil fuels. Mineral deposits are decreasing in grade, requiring more energy for extraction per unit of metal. This is happening at a time when energy is becoming more expensive and inelastic in supply. Technology development in mining is comparatively slow, requiring enormous amounts of capital. And economies of scale is the only way they've been able to survive. So hopes for future technology breakthroughs to somehow deliver on more commodity resources don't seem to consider the nature of what mineral resources are left. And the current ecosystem has no concept of its dependency on minerals and does not consider long-term concepts like continuous growth in production against finite resources. So the snapshot answer is our industrial ecosystem is minerals blind as well as energy blind. That is changing. Current thinking has seriously underestimated the task. Nuclear is vital to keep the industry going, but cannot be scaled up as the universal energy source. Biofuels may be the only way to power aviation and plastics, but cannot be scaled up to replace petroleum. Battery chemistries other than lithium-ion will be developed, each with different chemistries, each requiring different minerals as sources. What are they? Can we go and get them? Current mineral reserves are not adequate to resource metal production to manufacture the generation of renewable energies, technology units. Current mining is not even close to being appropriate, and the mineral reserves are also nowhere near enough for what we need. Metals of all kinds are about to become much more valuable, and so we're looking at an evolution of the industrial ecosystem, and its market is likely. So there will be a renaissance in exploration, as we need to go and find some more stuff, but we require time to do it properly, and that's what we probably don't have. So there's a coming renaissance for the exploration and the mining of metals. Okay, Ketos, which is finished for thank you. So, questions? Are you still there?
Wow. Thanks, Simon. This is great. And we have questions online, which I believe you probably have access to, so you can browse them. But we also have questions in the audience. Maybe, I don't know, we'll take turns from alternating between online and in the audience. But yeah, Steve.
Thanks, Simon. Fantastic talk and terrifying at the same time. I'm already wondering about my 3 girls and what life they have ahead of them. The aviation issue. I've got two comments, which I'd like your feedback on. Where aviation is going to get its fuel from. Have you looked at e-kerosene, which is a hydrogen fuel product that's emerging? And then secondly, your talk explains some of the immense amounts of money that are being poured into fusion technology. And have you considered, what are your thoughts about that as being a solution to the future?
Okay, aviation first. I used what I could actually get sensible data from. That there's lots of concepts out there that are able to promise a lot, but they're very light on information that was defendable. So there are a number of products. Yes, you can make kerosene as a hydrogen byproduct from the hydrogen economy, but you've got to make the hydrogen first. So I did a study to show the size of the hydrogen economy. That in its own right is going to be a logistical nightmare, and it's very simplistic. It doesn't include things like storage and transport. So this whole report is very, very simple. In fact, a lot of these questions are answered by the calculations are simple and they don't include everything. So no, I didn't include that. I did actually, if we can have aviation fuel in liquid form, then it will work. You can't have a hydrogen fuel tank on an aircraft because it has to be round, a big round cylinder. And so it's not going to fit in the wings. So the tank has to sit in the cabin with the passengers, which vastly cuts down the capacity to operate. And so remember, yes, there are electrical aviation systems out at the moment, but they tend to be small planes and they're short range. They're not going to carry 500 people 8,000 kilometers. As a fusion, yes, I did look at fusion. So fusion has always sort of been like 10 years away for the last 50 years. There's a lot of hope that fusion will come through. If they do get fusion together, and some of the technical things that they're trying to overcome are enormous. Like my hat's off to them to actually get as far as they have. So let's say someone works out fusion tomorrow. At the moment, we can build a coal-fired power station in, say, 5-6 years. And we know very well what to do. It's a well-oiled machine. To get to the point where we can actually produce a fusion nuclear power reactor in anything less than 20 or 30 years is going to take a while. So now we're back to time. So I like the idea of fusion, but you've actually got to show me a viable industrial scale unit before I can actually include it in a study like this. I also considered 4th generation nuclear power, same thing, but the simulations included that. And I wanted to include thorium, but I couldn't actually sort of get the necessary data to complete it. All right, how did I estimate the journey lengths of battery capacity? So what I did was I started at the end and worked my way backwards. Number of vehicles and their size, and I estimated the kilometres they would travel in a year. And so to do the same work if the system was electric, like say you had an electric vehicle, let's say a passenger car, and there was an estimate of how many kilometres it actually traveled in a year. If it was electric, how much charge time, if it was able to consume a certain amount of power per kilometre or per 100 kilometres, how much electrical power would it need to do that? And so that was just the sum. It didn't include any of the sophistications of energy of charging. It was actually quite a crude calculation. But when I got audited, they couldn't find any way to improve it or fault what I did. I don't appear to have included materials required for foundations for wind turbines. No, I didn't. So cement and reinforcing steel, I did actually find some information for that, but one of my review panels said that the information I had collected was inconsistent, and so we agreed to leave it out. So yes, it'll require more materials again. What do I think governments will do when prices of power and energy spiral out of control? I suppose they'll have another meeting, and maybe they'll release a memo. I don't know, I'm very cynical about what they might or might not do. They're not that smart. I don't know. Okay. Do we face reality, increased research?
I realize
am I aware
no
of
one
this
here
discussion?
can
Okay,
see
so
questions.
last week I actually held a seminar at GTK, and I invited about 30 people from Finnish Parliament, but also from the Finnish industrial system, private sector, and academia. And I put them all in one room, and myself and Nate Hagens presented some very challenging information, and then went off to lunch. But when they came back from lunch, I told them that there's no such thing as a free lunch, and we went into a workshop. And so I gave them the problem and made them fix it. And so while they didn't fix it, they started to get their arms around these problems, and they actually had a frank and open discussion about the issues involved. So that's possible in Finland. They are slowly waking up to the minerals problem right across Europe, because now they're actually trying to get to the point where they're going to start producing enough. So discussions are being had, but they're not being had strong enough. Now, when I've presented this information, everyone I've presented it to have sat there like poleaxe hobbits, and not one single person has actually come back with a sensible pushback at all. And no one's been able to refute the numbers either, because it's been done from what's available on the market based on what's needed and a bottom-up backwards calculation. So the work I'm doing has actually generated a lot of discussion. I would like to see more of it. I do think the net position of countries like China and the United States and Germany and France, they're too big. They make their systems are huge, and from a biology point of view, the size and complexity of a system is related to the energy you put into it. If the energy reduces, the system must shrink in size and it has to become less complex. So we might see these large economies balkanize as a consequence of a low energy future. That is not something that you can really tell a politician. So they've got to observe it for themselves, and you've got to mentor them after that. Have I considered the potential for industrial energy times of flexibility? No, I haven't done anything like that. At the moment, it was just a straight calculation. The idea is that someone's going to pick up my report and say, brave attempt, but we can do better. And then someone's going to actually do a more sophisticated calculation or a series of works. All right. Any other questions?
Sorry, Simon, it's Neville Clint here in the audience. Thank you very much for the presentation and the numbers that you've put together, because they're incredibly helpful for raising these issues with the various stakeholders that we deal with. And I am always surprised in those audiences exactly of what you said, is how often there is no connection with actually what's required to achieve a number of goals that people are signing up for. So net zero by 2050. And I've now put a box in all my presentations that I call the miracle box. And it happens in about 2040. And suddenly we just flick across into renewables. I think the other component, there are two things which I'd be interested just to see what you thought about. One was we've started doing some work through Rick's Complex Ore Bodies program, looking at the impact of these increased number of mines on the environmental impact. So they all come at a cost, and what it'll take to rehabilitate. I mean, if you just look at the copper expansion, that's significant. And then the other one is, when I finish up, my conclusion is the challenge is how do we change people's consumption? Because everything we consume requires energy, and we have to significantly reduce that. Have you had a look at what level of consumption would be needed and by whom to try and address this in an alternative way rather than a just replacement, but actually we have to do replacement and reduction?
So the first question is the simple answer that everyone comes to: if we need more minerals, we should go and remine our tailings dams. Now, I'm involved in a number of research projects that is actually looking at that. And yes, we can extract metals out of tailings dams, but all the good stuff's already been taken out, and especially economically viable stuff. And so the volumes required compared to the effort put in for mining of tailings dams is not going to be good enough to replace conventional mining. And that is something that another thing we need to come to terms with. As for the environmental fallout of all these large-scale industrial systems, I haven't actually sort of put together numbers to show that, but I do believe it's going to be extraordinary. I think there's going to come a point when mining is going to eclipse industrial agriculture in its impact on life systems on the planet if we keep going. I don't think we will keep going because we don't have the energy. Energy is the master resource. As for consumption, I got a flaming from, I think, I was presenting to Wilton Park, which reports to the British House of Lords. And I got a flaming from one of the guys on the call. Says, like, you're presenting a very negative picture. You've got to give us a solution, otherwise we're not going to talk to you. And so I went away and developed a possible change in how we might actually go about changing our relationship with minerals. And so I'm going to type an answer in the chat if I can. And so that's a report that was actually written where we restructured the circular economy in its current form is not going to work. It's simply not practical. And so I've put a counter answer to it in how we might manage our resources more effectively. In terms of consumption, at the very heart of this, there's going to be a complete change to our social contract of what we use metals for. And when we design things, we need to design them to last. At the moment, we design them to wear out so we can buy them again. And they're not designed to be recycled. So they're designed to be thrown away. And so at the heart of our design culture and what we need things for has to change. That is a very complicated discussion. And you can get into dangerous waters very quickly because it's not data supported, it's more emotional. And so, no, I haven't actually sort of done anything of consequence there. In fact, I've avoided it so far. Maybe someone else can do it.
Simon, it's Tim here. Just a couple of quick things. As I said at the beginning, I was privileged to have read part of this report already. You kindly sent it to me, but I have to say it was just as terrifying the second time around. So I agree with Steve. Two quick questions. One is I'm reminded of the infamous report, the Limits to Growth, issued by a number of distinguished economists in the 1970s that essentially took data like you've done and predicted that we would run out of all important metals by about the year 2000. Clearly that didn't happen. They made the undergraduate blunder of assuming that the only metals in the ground were what the mining companies reported as reserves.
which clearly is a small proportion of what's really there. So firstly, I assume you haven't made that mistake. My second question is a more serious one. You essentially have produced data, if even half of it is right, that completely destroys all of the current plans, entrenched positions, ideologue situations, and so on, which means you are going to get viciously attacked. And it sounds like it may have already started. What's your plan for dealing with that? So 2 questions, the old problem of limits to growth and what's going to happen next to your report.
So the Limits to Growth report, as it was released, they did an update in 2008 where they looked at it, where they projected the data from 1970 to the year 2000 on the standard run. And the data projected onto that fits roughly the same pattern that shows conceptually the Limits to Growth report was conceptually correct. What they got it badly wrong was when. It's a trend that goes across a century. So at what point do we hit a problem? I don't think anyone knows that. So all I've done here is, if we think we are going to replace the system as it is now, how much metal will we need to manufacture the needed number of units to do that? So the obvious outcome is we won't do it. We will have less technology units. We'll have to shrink the system somehow. And so the future will not look like anything like what I presented, because we've been moving in a particular direction with our industrial ecosystem. And so the idea of, say, growth economics, for example, is about to be phased out whether we like it or not. So the economic model behind materialism and consumerism and the social constructs associated with that will have to go. So we've got no choice there. And so the purpose of this work is to show the shortcomings of the existing paradigm. So what will happen is we've got to make a better plan. Once we understand our true boundary conditions, what could we really do? As for, yes, there's been a few screams of pain when I presented this, but because I've actually presented data on stage from blue chip sources, in fact, I've used their data, the pushbacks have not been very effective. I have been thrown a few challenging, not questions, but challenging comments along the lines of, "You're a very naughty boy, could you please stop doing that?" It really is that level of pushback. My management understands, and they back me, and that's all I need to know. The way I convinced my management was pointing out that in 2024 or 2025, the captains of industry in Europe who are making electric vehicles and their batteries will turn to the geological surveys of Europe and say, "Why did you not tell us about this very obvious problem?" Now, Finland in particular has a portfolio of battery minerals, more so than any other European survey. So we're going to be first on the chopping block. And I pointed this all out to management. They said, yeah, okay, we've got a problem. And they gave me permission and a mandate to go off and explore this in any way I see fit. And so their support's been remarkable. Now, I do have a plan. If it does get too hot, I've already got a series of projects I've lined up. I'm working in battery chemistries at the moment, so the recycling of battery chemistries, and also geometallurgy is still running. If it does get too ugly, I'll just quietly leave and move on to another frontier. First frontier to look at is rehabilitating land that's been sterilized through industrial agriculture. So for every bushel of wheat that goes to the market, 0.8 cubic meters of soil is sterilized through current methods, and this is our land degradation. So the idea is to get GTK to partner up with a group that actually does life systems like Luke or NRRI, and do the mineral balance in the soil, and we'll get them to reestablish the food web. The second thing I was going to look at was to look at the historical data for over the last couple of 100,000 years of how our climate has changed, and see if I can actually decouple the industrial era from that. So And there is a very interesting project that's actually on the books at the moment where I'm actually developing what I call the minerals atlas. So all minerals going into metals that will then go into a product across a value chain. I'm looking at a way of characterizing it so we can determine where in the value chain it is based on the data, and to look at the spectra from, say, XRF and XRD to try and track as we've moved along those value chains. And that's actually the next generation of bat circle. So yes, I do have an escape plan. So far, I haven't needed it, though. If I was going to get shot at, it would have happened by now, because this has now been running for a couple of years.
I hate interrupting flow because this is great discussion, but we do probably need to wrap up. I want to make an executive decision and say, because there are still a few questions online for you, so I encourage these people to perhaps reach out to you personally, but I do want to leave with just one more question. I guess it's kind of rolling the dice. What do you think about the long-term impacts of carbon capture storage? The storage capacity is huge, but finite. Is it considered a sustainable mitigation method?
So the systems I've looked at so far for that, I've just attended a couple of seminars, and like everything else, it works on a small scale. But is it viable in terms of the effort that you put in compared to the effort you get out? How effective are these systems? And how much carbon will you consume by deploying them? Right. So how effective actually are they? So a lot of these things are actually have trouble in scaling. And so I think the simple answer is we're only part of the way there, and more needs to be done. And now we're back to we don't have enough time. Of course, someone could prove me wrong. And if they do, great.
Thanks, Simon. It would have been great to have you here present in person, because I think we could have probably go on talking forever. Let us thank you one more time. This was fantastic.
Okay.
And next week, we are back to a seminar here at the Lecture Theatre, and we have a team from Mintech from South Africa, as led by Dr. Mehdi Safari, and they will discuss technological assessments on recent developments in fine and coarse particle flotation systems. Thank you.